Okay, so examples of hyperbolic PDEs are d phi dt plus c d phi dx equals 0. Second order wave equation. Okay, now let's look at what a hyperbolic equation is. So this is the introduction, which we did some time back. We only looked at second order equations. So there's a order 2 there in the PDEs, and we classified them based on b square minus 4ac. So b is the coefficient, the constant term in front of d square phi dx dy. Right, this is only for second order PDEs. However, what I've written down here seems to violate that. So this is okay. We can actually check that b square minus 4ac is actually greater than 0 for this one. It's greater than 0 for hyperbolic. But how come this equation, which is a first order equation, is actually a hyperbolic equation? It turns out that you can show that that first equation is actually the same as the second equation, which I'll just show quickly. So how to show that this is a second order equation? Slide 1 and 2. So it can be shown that 1 gives or is the same as 2. Okay, let's see how to do that. So you start with d phi dt equals minus c d phi dx. So this is from 1. Just wrote down the same thing, but just move things around. Okay, now what we'll do is we'll take the second derivative of this. So differentiating both sides with respect to time. So d square d phi dt square equals minus c. C is a constant, so I can pull it out. Dt d phi dx. Okay, just taking the derivative. Now there's a rule in differentiation which says that the order of differentiation can be reversed. So we can write this expression as minus c d dx d phi dt. This is order of differentiating can be reversed. So now what I'll do is I'm going to sub in the value for d phi dt. It's nothing but this. So minus c d phi dx. If you want to, let's call this 3. So from 3. Okay, now we see that's nothing but c square d square phi dx square, same as 2, which just proves that d square phi d phi dt equals minus c d phi dx. This expression is the same as this expression after you do all this manipulation. So it is actually a second order equation. Once it's second order, we can use the classification we used to figure out if it's elliptic, parabolic, or hyperbolic. In this case, hyperbolic, because b square minus 4ac is greater than 0. Okay, so that's just the types of equations we'll be using. Now let's go to the numerical solution part of it. How do we solve for the solution of the second order wave equation, for example? Okay. Now, before we solve it, let's just see what are the conditions we need in order to solve it. So to solve this, we need, so it's a second order equation in time and second order equation in x. So it clearly needs 4 conditions. 2 of those conditions should be on time and 2 of those conditions should be on x. So the conditions on time are usually the initial conditions. So two initial conditions. They would be of the form t equals 0. We know something about phi. Let's say that phi is some function of x. We also need another condition, which is typically on d phi dt. That is maybe some other function of x. So d phi dt is alpha 2 of x. Okay, we also need, because there's second derivative in x, we also need 2 boundary conditions. Okay, so for example, x equals L, so x equals 0, phi is given to you, say beta, so it's Tx greater than 0. And then x equals some length scales, we have phi equals beta 2 t greater than 0. Okay, so those are the boundary conditions. We can use finite difference, like we've always done. So what I'll do is I'll use the central difference for t square phi dt square plus 1 comma j minus 2 phi I comma j plus phi I minus 1j divided by delta t square equals c square I comma j plus 1 minus 2 phi I comma j plus phi I j minus 1. That would be delta x square. Just a forward central difference on the second derivative. Okay, so what we need to do in here is we are typically trying to solve for the variable phi as a function of time. So we're typically interested in this quantity. Okay, and this is usually given. All these things are given. You know what the phi is at the current time and j. You know what happened 2 time steps back. You also know all these values. So anything at time t equals I and before is known, and you're interested in knowing what happens at t equals I plus 1. So what we can do is we can solve for phi I plus 1 comma j. Is simply minus phi, sorry, I minus 1 j plus c square delta t square divided by delta x square phi I j plus 1 plus phi I j minus 1 plus 2 1 minus c square delta t square divided by delta x square phi I comma j. So this method has it's stable as long as 1 minus c square delta t square divided by delta x square is greater than 0. Okay. C delta t less than 1. It is also known as the current condition. It's called this one. Yeah. The name is called COURANT. Just the name, yeah. Okay, so it's clear we need to use this formula, which I wrote down, right? Okay, so let me just copy that. So now let's look at this formula. If you put, let's say if you put I equals 1, okay? If you put I equals 1, you'll have something like phi, well, let's put I equals 0 first, right? We start with 0th index. So we have 1, j equals phi 0 minus 1 j. Now look at this first term. You have 0 minus 1, which is minus 1. That just doesn't make sense, right? You cannot have phi minus 1. So you cannot use this formula for I equals 0. Clearly, if you use I equals 1, it should work out. I equals 1, we have phi 2j equals minus phi 0j plus this condition. So I is equal to 1. So 1 comma j plus 1 plus phi 1 j minus 1 plus 2. I'm just going to write it down because I just want to see if I can evaluate this. So it's clear that if you know this, then we can evaluate this. So you cannot use it for I equals 0, but you can use it starting from I equals 1, just because the way what you need in terms of phi. So we need to know what is the value of. So we need these values, right? We need this value, which is here. This is the value at time t equals, well, I equals for time, whatever the time is, but I equals 1. We also need the value at when the index I equals to 0. So these two values actually come from the boundary condition, sorry, from the initial condition. These conditions should give you the value for u 0 and u 1. So let's see how to use them. So first of all, let's start with our discretization. It's 0.25 for x and 0.1 for time. So let's put that in. So we'll use the notation ui comma j, where I equals time, the time index, j is the position index. Okay, so what we know is for time, we have delta t I, where delta t is (0.1). It's here 0.1, and we need to go all the way to 0.5, which means that we need to I needs to go from 0, 1, 2, 3, 4, and 5. So in other words, this will be 0, 0.1, 0.2, 0.3, 0.4, and 0.5. For x, we have delta xj, where delta x was 0.25, and then x goes from 0 all the way to 1. So in that case, j would be 0, 1, 2, 3, and 4. So that xj would be 0, 0.25, 0.5, 0.75, and 1. Okay, that is just setting the grid. Okay, now let's revisit the initial condition and the boundary condition. Okay, so we need to be able to write this condition in terms of I and j, because there's no, we don't really understand ux comma 0 in that sense in which it is written. So let's do that. So what it says is, here x is the second index, that's j. First index is I, and here I is what? It's 0, right? So it's 0 comma j. So u 0 comma j. So I just kept j as j because this is a function of x. X is, in this case, j, second index. Okay, so now I need to evaluate this. So for j equals 0, that is at 0, we have x of j, so 0, 0 comma 1, so that will be x1. When I put x1 here, I have 0.25, 0 comma 2 would be 0.5. Okay, that completes x from 0 to 0.5. Then if I go to 0 comma 3, the index 3 is this one, 0.75, but 0.75 is in this range, so it will be 1 minus 0.75, which will be 0.25, and 0 comma 4 is basically again this range, so it's 1, so 1 minus 1 will be 0. So in other words, this condition, these conditions are here. And this condition are here. Okay, so that's one of the two initial, that's the initial condition on U. There's another initial condition. That condition is here. It's du dt is x comma 0 is 0. Okay, so let's write this down in terms of I and j. So this one is going to be, I'm just going to use the forward difference. You could use something else, but forward difference seems the most easiest one. This one is u. So remember, it's something divided by delta t, and we need to iterate over the time index. So the time index is the first one. So I plus 1j minus u ij. Oh no, that's not right. So time is 0, my bad. This is only in the first index. So it will be 1 comma j minus u 0 comma j, because it's for any x. So any x is basically the second index. X can take any value, so j can take any value, but it's only for the first and the second values of u in the time index. So it will be u1 minus u0. Okay, so this should be equal to 0. And this actually gives me this interesting thing, which is u1 comma j is u0 comma j. It's saying that whatever u 0j is, that's the same thing given to u1j, which means that you just have to essentially copy this thing down here. So u1 comma 0 is 0, u1 comma 1 is 0.25, u1 comma 2 is 0.5, u1 comma 3 0.75, so 0.25, 0. Since u10 is u0, u1j is u0j. So you just copy the same value. So this is what I got, and then this is the other one. Okay, so that takes care of the initial condition. These are the ICs. I see. We still have to go through the boundary conditions. Yeah, actually, those are kind of simple. See the boundary conditions. So boundary conditions are here, this one. This is the boundary condition. Yeah, I think I just need enough space. This much space is enough. Okay, these are the boundary conditions. So let me convert them into I and j, index I and j. So u0 comma t would be the first index is time, so I keep it as it is. The second index is x, that is 0, so that's 0. Again, time, the first index remains as is. The second index is 1, so I need to locate the value of j when x is 1. So xj equals 1, we should use the fourth index, right? So these are, see, 0, 1, 2, 3, 4. That's for j equals 0, 1, 2, 3, 4. So the fourth one is 1. So I need to just put here 4 equals 0. Okay, so that's what we would need to solve. And then one more thing which is needed, let's compute. Let's just do it on the new page. So we need to compute the current condition, the value of C. C delta T divided by delta X, the current condition. This is, by the way, the boundary conditions. Let me write it down. PC. Okay, so the current condition is C delta t divided by delta x. C is, I believe, 1. So C is 1. Delta t is 0.1. Delta x is 0.25. If you crank the numbers on that, you get 0.4. So since this is 1, less than 1, we are good to go. We can use the formula I wrote down earlier. So now the formula, which is right here, is it here? I'm just going to copy this formula down, but I'm going to replace the value of c. It'll save me some time. I just put the value of c delta t delta x squared and write the formula down. So the formula produces to, let me just actually write down the whole thing. I plus 1j equals I minus 1j plus c squared delta t squared delta x squared j plus 1 plus ui j minus 1 plus 2 times 1 minus c squared delta x squared uij. And so putting this value of 0.4, we have u I plus 1j equals minus u I minus 1j plus 0.16 u I j plus 1 plus u I j minus 1 plus 1.68 u I j. Okay, so this is the formula we can just use in our calculations. As I said earlier here, you cannot use it for I equals 0. You can only start with I equals 1. So let's start with I equals 1. So let's put I equals 1. When you do that, we have 2j equals minus u 0j plus 0.16 u1 j plus 1 plus u1 j minus 1 plus 1.68 u1 j. Okay, so I'll have to circulate along j. Now j is the index for x. It goes from 0 all the way to 4. Okay, so j goes from 0 to 4. But there's a catch. You cannot just put j equals 0 to 4. If you put j equals 0 here, then you'll end up with 0 minus 1, which is u of 1 comma minus 1. That doesn't make any sense. There's no minus 1. So you cannot put j equals 0. You have to start with j equals 1. Okay, you actually know the value of anything I comma 0. It's one of the boundary conditions. You already know that, so you really don't need it. You already know the boundary condition here. This is j equals 0. And you also know j equals 4. So you can't even put 4 because, again, when you put 4, you'll end up with 4 plus 1, 5. There's no fifth index. So you just have to go from 1 to 3. Okay, so we have to write this down for j equals 1. u21 equals minus u01 plus 0.16. u1 j plus 1 would be 2 plus u1 j minus 1 would be 0 plus 1.68 u1 comma 1. Okay, now we make substitutions. We need to figure out what these values are. Some of them, all of them actually, will something you'll be able to figure them out. So let's do that. u of 0, comma 1. Okay, so the index time is 0. Looks like it's a initial condition. Let's see if we can find it here. It's here, 0, comma 1. It's 0.25. So 0.25. u1, comma 2. Let's go back. 1, comma 2 is 0.5. 1, comma 0. 1, comma 0 is 0. 1, comma 1. 1, comma 1 is 0.25. That's it. So everything is known, right? Plus 0.16 plus 1.68, the negative side. So the answer to this is 0.25. Then we put j equals 2, u2, comma 2 is minus u0, comma j is 2, so 2 plus 0.16, u1, 3 plus u1, 3 minus 2 minus 1 is 1, plus 1.68, u1, comma 2. Again, u0, comma 2. 0, comma 2 is right here, 0.5. 1, comma 3. 1, comma 3 is here, 0.25. 1, comma 1, 0.25. 1.68. 1, comma 2. 1, comma 2 is here, 0.5. 0.42. J equals 3. We have u2, comma 3 equals 0, comma 3 plus 0.16, u1, comma 4 plus u1, comma 3 plus 1.68, u1, comma 3. Okay. Okay, so let's look at find what u0, comma 3 is. 0, comma 3 is right here. It's 0.25. 1, comma 4. 1, comma 4 is 0. 1, comma 3, 0.25. Yeah. You mean here? Which? This one? There's a mistake. Yes, it should be 2. Right? Yeah, my bad. U1, comma 2. Let's see, 1, comma 2. 0.5. My bad. Yeah, good catch. 1.68 u1, comma 3 is 0.25. So this answer is 0.25. So it just helps if you just tabulate the results. So what we found is u2, comma 0. Okay, u2, comma 0 is not over here, but it is actually here. The boundary condition 2, comma 0 and 2, comma 4 are both equal to 0. 0. u2, comma 1 is this is something we computed. It's 0.25. u2, comma 2 is 0.42. u2, comma 3 is 0.25, which is this value. And u2, comma 4, which I showed you earlier here, this one is 0. Okay, so this just gives you the value for I equals 2. Okay, but we need to go all the way from I equals 5. So what you'll do is you will go and repeat this process. You will do this for I equals 2, I equals 3, I equals 4, and that's I equals 4 and I equals 5. Okay, and then you will just get this, and I'll give you the table, but you can check maybe 2 or 3 of these values for 2 more values, for 2 more values of u, and then stop. But let me give you the table. So you will see that you will have to use these values in order to get the solution for I equals 3 and so on. So here is the tabulated result. So let me put a note here. So continue for I equals 3 and 4, right? Because when you reach 3, you'll automatically put I plus 1 is going to be 4 plus 1, 5. So you just need to do 2 more indices. I already did it for 2, but you need to do for 3 and 4. Okay, and then check your solution against mine. So this is the solution. Zero, 0.0, 0.1, 0.2, 0.3, 0.4, 0.5, and then x 0, 0.25, 0.5, 0.75, and 1. Everything at 0 is 0. Everything at 1 is also 0. We were able to compute the solution for, maybe I should put this. We already computed the solution for the first index. This was basically the initial condition. It was essentially this table. You have to put this there, 0 0.25, 0.5, 0.25, and 0. Okay, the second index, 0.1, is something we also computed here. It's this one. 1, 0, 1, 1, 1, 2, so 0 0.25. It's the same as the first one. So 0.25, 0.5, 0.250. Okay, now is the time when we can look at our solution, which is the third row there. The third row is something we computed here, 0.25, 0.42, which is also summarized here. So we only need these 3 values. 0.25, 0.42, 0.25. Okay, these I have not computed, but you will compute them. What I get is 0.2372, 0.2856, 0.2372. It's symmetric, so you'll see the same solution for 0.75, 11942, 0.1357, 0.1942, 0.1108, 0.0045, 0.1108. Okay, so you're expected to create a table like this.